So on the speakers circuit, we refer to this slot, the one before the lock note, as the graveyard shift. And this is because we see a little bit lower attendance because some of the attendees have already gone home, especially the ones that had to travel or do a workshop. So thank you so much for sticking around. But it's also because after back-to-back social events all week, you're also feeling a little bit like death. So this is my first graveyard shift, and I actually wasn't supposed to be here. I originally had the slot bright and early, right after the keynote on Wednesday morning. However, this was me on Tuesday night. In the hospital, recovering from an emergency appendectomy. Now, I am pretty sure the organisers rescheduled me to the graveyard slot to give me the longest possible chance to be fighting fit for my talk today, but I can't quite silence this little voice that's also hoping that this is a little bit of a fun joke. Let's give the graveyard slot to the woman that almost died on her way here. So you see, I landed in Copenhagen on Sunday, and with 8 hours, I was in the emergency room, and with 8 hours after that, I was having emergency surgery. Seems my appendix had probably already burst by the time I boarded my flight in Amsterdam, and had also caused a full bowel obstruction. So almost died is not an offensive exaggeration. Now, I don't want to dwell too long on this, but I would like to say that if you are thinking of giving a yellow or a red card today, maybe cut me a little bit of slack and go for a green card. I don't think that is too much to ask now, is it? So my name is Adele Carpenter, and I'm a software engineer at Trifork Amsterdam, where I work on projects for the educational sector. Now, this talk is a milestone for me, my 10th NDC appearance, and what better way to mark the occasion by not only almost dying, but by giving a talk with the clickbaity title that's probably going to make some of you feel a certain type of way. So who here identifies as a C# developer? Yeah, quite a lot of you. Yeah, and that's what I expected. And as a Java developer, okay, less, but a few, great. So it's okay to be in the minority. I mean, it could be worse. We could be Haskell developers, or worse, COBOL developers, or even worse, Vibe coders. I must say, though, that as someone that does attend a lot of Microsoft-centric conferences, I do feel like a little bit of an outcast as a Java developer sometimes, like almost embarrassed to admit the things I have to do to keep food on the table, which is hilarious to me, because if you spend enough time in both worlds, it becomes painfully obvious that we're basically the same. I mean, we shouldn't be fighting. We should be uniting against our common enemy, the people that believe that JavaScript belongs on the server. And that's the mission of this talk today, is to bridge the Java and C# factions a little bit, and to have some fun in the process. So this is a talk concept I've been mulling over for a little while, since I first started speaking in 2021. Now, has anyone seen this movie, which came out in 1999? Excellent. So this is the year we got the just-in-time compiler and the correct collections framework as part of Java 1.2. So it's 10 Things I Hate About You, loosely based on Shakespeare's The Taming of the Shrew. And one of the core plot lines is basically heartthrob bad boy chases disinterested girl. And spoiler alert, girl does fall for boy, even though he's frustrating, annoying, and quite possibly the worst. Frustrating, annoying, and quite possibly the worst. Can't imagine why this inspired me to write a talk about Java. So, as is often the case with talk writing or any creative pursuit really, you can have an idea, but not the substance that's going to take it from fledgling to fully formed beast. So, enter Mads Torgersen. Now, Mads is not a Java developer, at least not anymore. And for those that don't know, Mads is the lead designer of the C# language at Microsoft. So to C# devs, that makes him the king, and to Java devs, the enemy. So one of the cool things about being a speaker that usually gives more general talks is you get to speak for a lot of different communities, even if you aren't fully across the dynamics of those communities. And as an extension of that, you can end up having dinner with some rather important strangers. So earlier this year, I found myself having dinner with Mads. I'd been invited by our mutual friend, Rendell, and the three of us were speaking at the same conference. Now, Rendell, a true polyglot developer, giving the lock note, was relaying their experiences learning Zig and said something along the lines of, as fun as Zig and other new languages are, I just keep coming back to C#. It just has so many handy features that make it effortless for me to write good, performant code. Now, I actually naturally asked Rendell for an example, and Rendell offers up reified generics. Now, what are reified generics? I naively exclaimed, although the speech bubble on the slide here is probably closer to what I said. So Mads, the lead designer of the C# language, who I had just met and made an excellent impression on by asking who he was, patiently started explaining reified generics in C# to me. And when I asked what I thought was a natural follow-up question, what is the equivalent in Java, he even then more patiently explained that they don't exist in Java because Java has type erasure. And without skipping a beat, because he clearly knew who he was dealing with by this point, kindly explained what type erasure is. Now, this conversation encouraged me to go a layer deeper into language design and gave me the framework to explore what I felt regularly as a Java developer, namely frustration, confusion, and Stockholm syndrome, in a much more targeted way. Now, I want to make clear at this point what this talk is and what this talk is not, and who I am and who I am not. So I am a Java user, and I spend most of my day building and maintaining Java and Kotlin applications in my role at Trifork. And I'm not an employee of Oracle, nor do I have any close ties to them, so any opinions that I give are my own. And this talk, well, this talk is a warts-and-all look at some of the features of Java that are the most frustrating, but at the same time stay true to its overarching design philosophy. Build once, run anywhere, always and forever. And where it makes sense, I will compare Java's features and design choices with the equivalent ones for C#. Which means that despite its title, this talk is more of a love letter to Java than an outright mudslinging. So if you've attended this talk for an hour of Java bashing, then you're going to be sorely disappointed, and you're quite welcome to out yourself by leaving the room and dropping a green card in the box on the way out. And I'll wait. Now, I often get asked what my brand is as a speaker, and until I started writing this talk, I didn't really have an answer, and I probably still don't have a good answer, but there's one thing that I try to do above all else, it's to provide context. So why are we here doing what we're doing? Do we have to do these things this way? Are other industries or communities facing similar problems? And if so, what can we learn from them? So in the spirit of context, let's go back to the decade that arguably defined our entire industry as we know it, the 1990s. So it's 1991, and Sun Microsystems has just formed the Green Team, led by James Gosling, who's this one here. And in the backdrop of an exploding consumer electronics market, the team has started developing a small, reliable, portable, distributed, real-time operating platform. And what started as a C++ project has rapidly evolved into something else. It quickly became clear that C++ was an inappropriate choice, and a lot of problems that the team were facing could be most easily resolved by creating an entirely new language platform. So by 1992, Gosling and the team had a working prototype running Java, at that time called Oak, on this device here called the Star 7. It was complete with an animated touchscreen and Java's soon-to-be iconic symbol Duke, which is this one here. But after a few failed attempts in the electronics market, Sun pivoted to embracing the World Wide Web. You see, this was the time before JavaScript, and this is what I imagine the world looked like before JavaScript anyway. And what Java offered with its platform-agnostic implementation in this magical time and place was a way to safely run code coming from the internet right there in the user's browser, turning the static web into the dynamic web. So Java 1.0 and the Hot Java browser launched in 1995, and the tech world, to put it mildly, went batshit insane. Time magazine named it in its top 10 products of 1995, declaring it a kind of Esperanto of the internet. The first Java 1 conference, held in 1996, drew in 6,000 attendees and made bold predictions for the future, like your desktop as you know it goes away and becomes the internet. You can recreate your home computing environment at a kiosk in the airport. And my personal favorite, software is never out of date. Of course, all with the big caveat, once the network is fast enough. So to say adoption of Java was quick is an understatement. By the end of 1997, Java was running on 80 million desktops, and the flourishing Java developer community was estimated at about 500,000 strong. Now, 500,000 doesn't sound like a lot, but that was about 20% of all developers on the planet at the time, and that is a conservative estimate. And this adoption was at least partially fueled by a deliberate design choice by Gosling and Co., which is that the new language should be simple, object-oriented, and familiar. Simple? Really? How do we write hello world in Java 1 again? And if we just compare this to something like Python, although the fair comparison is probably with C++. And I suppose if we do compare these two examples, the Java code is a little bit simpler, right? It's a bit more explicit. But it's important to understand that when the designers of Java said simple and familiar, they were acknowledging that the expected early adopters of Java would already be familiar with C and C++, and that the learning curve for those developers should be relatively flat. Gosling and the team further focused on keeping what worked in C and C++ and leaving what didn't, in the context of what was at the time modern object-oriented programming. So I suppose if I was giving this talk 25 years ago, the title could be C++, so Java didn't have to. Now, in addition to simple, object-oriented, and familiar, there were 4 more guiding principles of the design of Java 1.0, which from now I'm just going to call Java 1, all right? But before I take you through those, I want to introduce you quickly to Smalltalk, Mesa, Seda, and Xerox PARC. And no, these aren't 90s agro-tech bands that your kids have just discovered and that your neighbors are complaining about. Smalltalk, Mesa, and Seda are programming languages that were developed at the Xerox Palo Alto Research Center, or Xerox PARC for short. And yeah, when I say Xerox, I mean the company that brought us this. The photocopier, of course, not the woman. So Xerox PARC was established in 1970. You never know which jokes are going to land. To explore cutting-edge computer science and electronics to support Xerox future tech strategies. It was supposed to take Xerox beyond photocopiers. And technically, it did. This is the Xerox Alto, one of the first personal computers, and it carried a bunch of innovations, such as a graphical user interface, a mouse, and Ethernet networking. Now, computing urban legend has it that Jobs and the Apple team were inspired to develop the Macintosh after a visit and a demo at Xerox PARC, which, given that we're in 2025 and Apple is one of the largest companies in the world, and Xerox, well, isn't, could carry an ounce of truth. Anyway, this talk isn't about Macintosh or Apple. All this to say, though, that Xerox PARC heavily influenced modern computing as we know it, and this includes Java and C#. So for example, Smalltalk, developed in the 1970s, was one of the earliest and purest object-oriented languages. So in addition to Eiffel and Objective-C, it really put object-oriented principles at the heart of Java. Mesa was the second language to come out of Xerox PARC, and its main contributors to Java were structured exception handling, concurrency constructs, and portable bytecode-like execution. The third Xerox PARC language, Cedar, is a systems programming language built on top of Mesa in the early 1980s. As a language, its primary influences on Java were automatic garbage collection, modularity, and type safety. But the really cool thing about Cedar was that it came with an integrated development environment, including a compiler and a debugger. This heavily inspired the tool suite that shipped with Java 1 and has absolutely shaped the way that we continue to work as developers in 2025. So on to our second design principle of Java 1. Java should be robust and secure. One of Java's most notable moves was to step away from manual memory management, as done in C and C++, and toward automatic garbage collection. And this contributed to the robustness of Java by reducing memory leaks and presence of dangling pointers. It was a huge innovation and became the approach for many languages that followed, including C#. Now, as I just mentioned, Java didn't invent, but merely borrowed the concept of automatic garbage collection from Cedar and Smalltalk. Java made it better, though, through innovations such as generational and stop-the-world garbage collection, along with heap segmentation, safe points, and write barriers, all of which were adopted in early versions of C#, although not always implemented in the same way. Strong compile time and runtime type checking also helped to prevent errors in programs written in Javas, and these features were inspired by Cedar and Mesa. Security in Java got a boost by its introduction of the sandbox model, which restricted untrusted applets from performing potentially dangerous operations such as I/O or network access on the user's system. In addition, a bytecode verifier ensured that the bytecode did not violate Java's safety constraints before it was executed. Design goal 3, Java should be architecture neutral and portable. And the biggest wins here were compiling the code written by the developer to Java bytecode and the Java virtual machine specification, or JVM spec. So with these two features in place, the code the developer writes is compiled to a platform-neutral bytecode, which is then executed on the JVM. And each operating system has its own implementation of the JVM that adheres to the JVM spec. And this provides for a consistent runtime environment across operating systems. And this approach was adopted by C# with the Microsoft Intermediate Language and the Common Language Runtime. Portability was less of a concern for early versions of C#, given the focus on the Windows platform, but we did see cross-platform capabilities improve with .NET 5. Design goal 4, Java should be highly performant. The Java bytecode instruction set was designed to be compact and efficient for interpretation, and Java 1 also laid the foundation for the just-in-time, or JIT, compiler. And a JIT compiler is an optimization that converts bytecode into native machine code at runtime. So while the JIT compiler was not included in Java 1, the design gave space for future implementations to support just-in-time compilation. On the flip side, C#1 did ship with a full implementation of a just-in-time compiler, which meant that C#1 was faster than Java 1's interpreter-based JVM, you know, when C#1 launched 6 years after Java 1. So, design goal 5, Java should be interpreted, threaded, and dynamic. Java 1 introduced multi-threading that just worked with the building blocks of thread class and synchronization. So like automatic garbage collection, this was a pretty innovative feature for the time. And given the focus of Sun on the World Wide Web, multi-threading allowed for a high degree of interactivity for the end user as the language supported many concurrent threads of activity. And the threading model that Gosling and co. chose was based on that of Cedar and Mesa. And one last thing to add here is that while the Java compiler is strict in its compile time static checking, the language and runtime system are actually dynamic in their linking stages. So classes are linked only as needed, which means classes can be loaded dynamically at runtime via the class loader, allowing the system to adapt and extend itself without recompilation. C# supports similar functionality, albeit through a different means, using reflection assemblies and optional dynamic typing rather than a built-in class loader system. But despite this different approach, though, the result and the underlying philosophy are similar. So let's put those 5 design goals up again. So what do you think? Like, do these seem like reasonable goals? Like, do you think the Java team succeeded? Do you think these goals are maybe still relevant today? And so if these goals are so good and the team did so well in meeting them, then why do at least a third of you have Java-related hate coursing through your veins? Because to me, this seems kind of silly, especially when we consider that C#1's design goals were met by looking like Java. Engineering is all about hard decisions and trade-offs, and it's completely reasonable to believe that the Java development team made some wrong ones over the years, in some cases at least. So let's start with a decision that in my experience gets the most impassioned response from C# developers. I'm speaking, of course, about type erasure. Now, if we're going to get so emotional, then we should understand what we are getting emotional about. So what are reified generics and type erasure, and why do they matter? So first, a quick intro or refresher on generic types, which I think is most easily done here with a code example. So in Java, we declare a simple class box, which holds one value of any type in it, denoted by T. So we declare the private field value, and then a constructor that takes that single value to create an instance. And the fact that this value can be of any type is what makes box generic. And then within the box class, we define 2 simple methods. One simply prints the value field, and the other prints the type of the value field. And here, the simple body of these methods. Oh no, I don't know how it could have possibly happened. I think I've mixed up my slides. This is actually the C# example. Shit, how could this be? I mean, clearly these languages are just so different. So different. So I know I've committed several heinous crimes in this C# example here. I mean, I'm using camel case instead of Pascal case, and that's just the beginning. But this isn't just terrible theatre. This code actually does compile and run. And before I show you, because I'm pretty sure you don't believe me, let's take a closer look at the box generic written in the elegant Java way. So defining it like this means we only need to declare one box class, not a separate one for each type, like integer box, string box, etc. Now, in the demo class, you can see that we use the same defined type of box to create an instance called intBox, which takes in a value of 42, and stringbox, which takes in a value of hello. So even in this trivial example, I hope you can see the power in this generic construct. Generics allow us to write type-safe and reusable code that works with different data types without us having to specify a concrete data type up front. And what about reified generics? Well, reified generics is a type system that makes generic type information available at runtime. So if we take a quick look at the demo, here's our box defined, and then we have our demo class here with our run method. So we're just going to run these two methods here, and now we're going to click run, and we're going to see the type printed out and then the value in the console. All right? Compiles and runs, okay? Now, if we take a closer look at the real Java example, not the pretending one, we can expect that print value works just fine. But in the print type method, the call to value get class is actually lying to us. Why the trickery? The fact is that in the runtime on the JVM, we just don't know the type or what sort of box, int box and string box are. So at runtime, we just don't know. So if we do an equality check, int box get class is actually equal to string box get class. The type information has been erased during compilation. And what this means is that at runtime, all generic types are treated as raw types, such as object. You can't access the actual type parameter simply because it doesn't exist. But don't worry, the compiler's got you covered, because if you do try to do an instance of check, for example, you'll get a useful compile time error. You won't get the type at runtime, you'll just get a compile time error. I mean, that's just as useful, right? And so in practice, this means things like Jackson, or basically any library that deserializes data into Java objects, needs to work around type erasure by passing in the expected type as an extra parameter. So you get something like this. Now, why on earth did Java do it like this? I mean, was it hubris? Ain't nobody gonna need introspection? Or was the Java team just lazy? The best yet very unsatisfying answer I can give you is deadlines and requirements. I know, I just heard all of your eyes collectively roll, but it is essentially what happened. So, two key players in the early development of Java were James Gosling and Bill Joy. James is on the left here, and he led the Java development team at Sun and is often referred to as the father of Java. And Bill is the co-founder of Sun, and at that time was the CTO. Bill is also the creator of the VI text editor, which he developed in the 1970s. So James and Bill often had very different opinions about the key features of Java and would famously argue at length about implementation and design decisions. And one of the things they couldn't agree on was the implementation of generics in Java 1. While Bill fought for the inclusion of generics in Java 1, James is quoted as saying, "As a sort of design principle for something lots of people were going to use, I'd rather keep the whole with a label on it than do something I know is wrong." And with the time window to launch Java 1 closing and the two men unable to agree, Java launched without several key features that Bill wanted, one of which was generics. And I think it's summed up well by this quote from a Green Team member, and the we in this quote includes Gosling. "We were right about needing to finish the language even though it had missing features. There was only about a 3-month window in which the whole Java phenomenon could have happened. We barely made it, but Bill was absolutely right about what Java needs long term." And one of the victims of this Esperanto of the internet Java phenomenon was generics, because by the time the team were in a position to add generics to Java in Java 1.5, a lot of Java code already existed in the world, and the team needed to stay true to their word on backwards compatibility. And I say needed here deliberately, and the reason I say that is because of the way the Java language evolves. Now, what do I mean by that? Well, the Java language has always evolved in consultation with the community. So Gosling admitted in a 2015 interview that before Java's public release, he could make a major, potentially breaking change to the language in as little as 10 minutes. No harm, no foul. But once there was a community around Java, real people writing real applications, he knew that it was necessary to involve the community in those decisions. Because in his words, if you make the wrong one, people could get very upset. So the Java Community Process, or JCP, was developed and implemented before Java's third birthday. And as it turns out, adding generics was one of the earliest proposed extensions to go through the JCP. And here's the proposal here. So Java Specification Request 14, or JSR 14, was one of three potential approaches to solving... Don't forget to drop your green card on the way out. So it was one of three potential approaches to solving the casting and runtime safety issues caused by lack of generics, and it was the one supported by Gosling and Son. So without any changes to the JVM spec, type erasure, as detailed in JSR 14, allowed code written before and after generics to be compiled into the same executable bytecode. A method class compiled using Java 1.4 could still be called by a class compiled in Java 1.5. And this desire for this level of compatibility and stability is a core philosophy of Java. Gosling admitted at the time that no VM changes means that some things become impossible, like introspection. In retrospect, he probably played down the importance of introspection on developer joy and ergonomics, for example. But given the fact that the year was 1999 and Gosling had his object-orientated hat planted firmly on his head, maybe he could be forgiven. But why was no VM changes so important in the first place? Well, at this phase in Java's evolution, multiple vendors were already providing VM implementations. So in the words of Brian Goods, Java language architect at Oracle, getting a dozen JVM vendors to agree on if and how type information would be reified at runtime was a highly questionable proposition. But independent of Gosling and Goods and VM implementations, at the end of the day, it was the community that signed off on type erasure in Java. Now, is that victim blaming? I don't know. But we can say this. We can say that at the given time, with the given amount of Java code in the world, and the given importance of backwards compatibility by the given community, generics with type erasure was the choice. And as for C#, well, the language designers over there made the opposite choice. They decided to update their VM and invalidate their existing libraries and all the user code that depended on it. Sure, the old code just worked, as the CLR allowed pre- and post-generic code to run side by side, another design choice. However, it was still necessary to recompile existing code in order to obtain full generic support. So, for example, if your generic supported code called a library that hadn't been recompiled, then it was your responsibility to manually cast to the expected type when dealing with that library. And that was a much more palatable option for the C# team than it was for the Java team at the time, simply because there was comparatively little C# code in the world. And additionally, and most importantly, there was no need to reach consensus with over a dozen VM implementation vendors. Adding generics to the CLR was a decision that Microsoft could make on their own. And I definitely believe that they made the right one. Reified generics in C# are a thing of beauty, and they're wonderfully engineered. They're also a wonderful example of the second mover advantage and the benefit of having a single corporate overlord. Now, I've been pretty compassionate and understanding of the Java language designers so far, but a girl has limits, and my limits are checked exceptions. So let me show you what I mean. So here are the signatures of two methods that each throw a checked exception. And if you call either method, the compiler will check that it has been handled explicitly at some point in the call chain. And this contrasts to C# and every other major programming language, which seems to just do fine with exclusively unchecked exceptions. Now, we're going to try to do something that's pretty common in a production system. We're going to fetch some data for a list of users, and then we're going to process it, and then we're going to return the result. But since I work in the education domain, instead of a list of users, I'm going to use a list of students, and we want to find how many students from our list are currently enrolled in local schools. So in this example, the school name is the most reliable way to do this. So first we fetch the school name of a particular student, then we pass the return string into a known school using a custom parser, and then we filter the schools that are inside the local district and get the size of the list that's left. Now, since we're iterating over a list, we can use Java Streaming API. Should be nice and clean and straightforward, right? Like this. And we can even make use of method references with the double colon notation there. Now, of course, you could use a single map rather than chaining, but I just chose to be super explicit about the steps. Now, the fetch requires an I/O operation, so it could throw a checked I/O exception. And because your colleagues are particularly conscientious, the pass school name method throws a custom checked school pass exception. This is all wonderful. Job done. Except you can't throw a checked exception from a Lambda in Java. So you're forced to handle the exception inside of it. So if you take a little bit of a naive approach and just simply do the bare minimum to keep the compiler happy, you wrap the offending methods in a try-catch, and you end up with this monstrosity. Now, I don't want to be too hateful, because part of me does understand what checked exceptions are trying to do. The intended use case of checked exceptions has always been for situations where we know up front what could go wrong, but we don't expect it to go wrong all the time. And the philosophy behind them is that the code that is calling the thing that might fail is going to have the best chance of knowing how to handle the exception. It has the context of what it is trying to do. Now, in the words of James Gosling, in Java, you can ignore exceptions, but you have to willfully do it. You can't accidentally say, I don't care. You have to explicitly say, I don't care. And given James' background working on operating systems, embedded systems, and VMs, this strong opinion on handling failures gracefully up front makes sense. But in a world full of closures and distributed data processing, it makes very little. And the fact that Java is the only mainstream language that has checked exceptions is very telling. And we can compare Gosling's statement with the one made by Anders Hallsberg when he was the chief architect of C#. Here, Anders is giving an example of a UI, but the quote really demonstrates their differing philosophies on exception handling. You don't want a program where in 100 different places you handle exceptions and pop up error dialogues. That's just terrible. The exception handling should be centralized, and you should just protect yourself as exceptions propagate out to the handler. Java developers have been complaining about checked exceptions for almost as long as Java has existed, but unfortunately it does not look like they are going anywhere, judging by this comment snippet from Brian Goods. So what do we Java developers do? Well, we don't need to do anything crazy like start using Kotlin or C#, both of which only have unchecked exceptions, because Java offers us the most elegant of very elegant workarounds. I'm speaking, of course, about the functional interface, which was launched as part of Project Lambda in Java 8. Now, a functional interface has exactly one abstract method and is the closest thing in Java you can get to a function that you can pass as a parameter. Meanwhile, C# has had delegates since 2005, but I digress. So we use this construct to define an interface and then to provide a default implementation for its one and only method. And once we have that defined, we then wrap our methods that throw the checked exceptions in a try-catch and rethrow as an unchecked runtime exception. This means that we don't have to handle the exceptions in our lambda logic, which brings us closer to what we would see in C#. And there's a thing of beauty, right? But if we take a look at the actual C# example, I have to admit the language of select where count gives me much better vibes than map, filter, to-list, and size. Link reads like it's for humans. Java reads it like it's for computers, or not just computers, computers and giant computer nerds. And there's no clunky boilerplate hidden in some utils package either. I mean, there's so much more room for activities. And in Java land, there's kind of this prevailing tolerance for creating boilerplate and dumping it in utils packages where we can. I mean, in the context of what we have and the conventions that Java has adopted, I mean, it's not so bad. Once it's written and it has unit tests, you can largely forget about it, but it's still code that you have to maintain, and it feels a little bit like cleaning your room by just shoving everything under the bed. And our tolerance for these language shortcomings as Java users is part of the problem. The successive libraries like Lombok and previously Guava really highlight that. The fact that those libraries exist at all is honestly quite embarrassing, and I think amounts to what I would call a code language smell. Still, I mean, could be worse. Sure, we dump boilerplate like checked wrappers and other helpers like object mappers in utils classes, utils packages rather, but at least we're not putting our business logic in automapper mappings.
You paid for that.
So, I wanted to wrap up this talk with a discussion of the most controversial design decisions of late and their associated fallouts. And I've picked two that stand out to me. But of course, if you want 100 opinions, ask 10 developers a question. So this is just my take, and I'm not speaking for anyone other than myself. So virtual threads launched in Java 21 in 2023 and promised us faster applications with only minimal code changes. Sounds great, all right? And while it might seem like it at first, it's not witchcraft either. You can think of virtual threads a little bit like multitasking, not in the way that pop culture describes multitasking as actually doing two things at once, but by the way it actually works, which is by rapidly switching our attention between a number of tasks at once. That 2 or 3 seconds we look up from our phone to focus on the TV and back again. So virtual threads do a similar thing to scrolling TikTok, watching TV, and talking to our partner about their day, only much, much faster. So virtual threads allow an OS thread to be utilized while it is waiting for a blocking operation such as I/O to complete. The improvement in throughput is then possible as the typical server application consists of a large number of concurrent tasks that spend much of their time waiting. And for the most part, virtual threads in Java 21 did deliver on this promise of better resource utilization, except for the cases where it didn't. So virtual threading came with a number of gotchas that surprised even Oracle, and the biggest one was thread pinning. When code running on a virtual thread enters a synchronized block, that virtual thread is then pinned to the underlying platform thread and cannot do any other work. If many virtual threads all try to enter synchronized blocks and get pinned, and there aren't enough platform threads free, the system can deadlock, where everything is waiting and nothing is running. So here is a pretty telling graphic from the Netflix blog on the previous slide, and you don't need to understand the specifics to get the message. So here we have the web server throughput shown by the blue line, and it suddenly drops to 0, and we see the number of sockets in a closed wait state increase steadily. And this has to do with the way that Tomcat creates virtual threads with each request. Now, Oracle are many things, but they are certainly not stupid. So they did foresee pinning as a potential issue. But what they did not foresee was the practical impact of pinning, not only in the Tomcat case, but in cases where even seemingly simple production systems would grind to a halt. And this was especially a problem for applications that relied on legacy third-party libraries that made liberal use of synchronized blocks. And the breadth and somewhat unpredictable nature of deadlocking from pinning made Java users cautious in adopting the feature. And the Oracle team were quick, Java quick, to rectify this by allowing synchronization without pinning in Java 24, 18 months later. Yet even if we subscribe to Java time, where 18 months or 3 release cycles is quick, I'm sure we can all agree that 10 years is a long time. I mean, 10 years is a third of Java's 30-year existence. But that's exactly how long we've been waiting for Project Valhalla, which I think is summed up really, really well by this YouTube comment. I hope so too, David. I hope so too. So David's really captured here what it truly means to be a Java developer, to be waiting for the present and sometimes even the past to arrive at some point in the future. Project Valhalla was announced with much optimism in 2014. It even has a battle cry, codes like a class, works like an int. So what does that mean in reality? It means we need to step back in time again. Now, I spoke at length already about how Java was developed in the early 90s to meet the demands of the fledgling World Wide Web, and now that shaped the development of the language. And just like any other software project, faced pressure to launch and to be one of the first to surf that internet wave. Now, at the time, a memory fetch cost about the same in terms of compute as arithmetic operations. So Gosling and Co., heavily inspired by Smalltalk, fully subscribed to the mantra that everything is an object. And this made sense. Object-oriented programming was the paradigm du jour, and rightly so. It brought significant benefits over the more common imperative styles of the time, such as modularity, abstraction, and reuse. But Java also needed to be fast, and the compromise reached was that everything the user can define is an object. So alongside user-definable reference types would be 8 primitives: boolean, byte, char, short, long, int, float, and double. So if your data didn't fit a primitive type, you modeled it as an object. And that was great, super flexible. The trade-off, though, was clear. Even simple value-suited types, like a point, just a simple XY coordinate, carried the overhead of heap allocation, an object header, a layer of indirection, an identity. But today, on modern hardware, the limitation isn't usually the size of the memory available, it's the performance hit of memory layout and indirection. Every pointer you chase costs cycles, every cache miss sets you back. So Project Valhalla aims to give Java developers the overdue tools to opt out of identity to achieve flatter and denser data layouts. So by flat, we mean cache efficient, fewer indirections, and by dense, we mean memory efficient. Data that belongs together is together. And the expected consequence of more cache and memory efficient code is a significant boost in performance. Now, how do you think that they're doing that? Keeping in mind that they've been working on this for over 10 years. They're doing it by introducing something really cutting edge, something Java developers have never seen before. Wait for it. Value types. How exciting! The past has finally arrived. And I mean, even Brian Goetz had this to say at the JVM Language Summit last year. We've been working on this 10 years, which is kind of appalling. If you watch the video, you can actually see the embarrassment in his face. But think back to to a time when you've had a stakeholder say to you, why is this taking so long? And what was your response to that? Did you try to explain the technical constraints maybe? I mean, that's certainly been my reflex. And it's a reflex because that's usually what's happened. You not only had to build the thing, you had to clean up the mess of the past before you could even think about building the thing. And perhaps, if you're really conscientious, you want the big thing that you built to feel natural to the user, like it had always been there. And that's Valhalla, Java's epic refactor. And in that same talk from Brian, he said the first 8 years were actually spent running experiments and building prototypes, basically deciding on an implementation. They almost had a complete implementation at preview stage and then threw it out. So they spent a lot of time unraveling 20 years of technical debt, because this epic refactor actually goes to the center of Java's type system. Valhalla not only delivers value types, it also delivers null restricted and nullable types, as well as primitive boxing, as outlined by these 4 Java enhancement proposals, or JEPs. So we have JEP 401, value classes and objects. This is available now as an experimental feature. We have JEP 402, enhanced primitive boxing. It's technically in preview, but it depends on null restricted value class types, which is actually still in JEP draft stage. And lastly, null restricted and nullable types, which is actually still a JDK bug report and not even in JEP stage yet. So in all practicality, after almost 11 years, Java users are still waiting to tuck into the meat and potatoes of Project Valhalla. That said, the real work in Valhalla has been in healing the rift between primitives and objects in Java's type system, and the bulk of that work has now been done to address the technical debt that has been holding Java back from fully embracing a more modern, data-driven and functional programming paradigm. A debt that grew larger when we got generics, as you can't generify a primitive, and a debt that grew larger still when we got lambdas, since the implementation of lambdas relies heavily upon generics. So, for example, instead of defining a simple function of input type T and output type R, or a predicate of type T in the streaming API, as we have for reference types, for primitives, we need a highly specialized suite of functions. Now, these are just the ones for int, and the same ones exist for double and also for long. So the ambitious sub-goal has basically been a more cohesive and ergonomic type system. Oh yeah, and the ability to handle all types, primitive, value, and reference, generically. Welcome to 2005. So, does Java still actually suck? I must admit, in writing this talk, I have at times felt a little bit like the wife of a deadbeat husband, like a little bit along the lines of, oh, you know, he had a really tough upbringing and he's really started making an effort. He has a job stocking shelves now and only plays video games 6 hours a day. Perhaps that's a little harsh, or maybe it's a lot harsh, but, you know, feelings are feelings and it's okay to have them. But I must say, writing this talk has exceeded my expectations in reigniting my love for Java. It's amazing how putting in a little bit of effort into understanding something before you judge it can do. Yes, I still wish Java had reified generics. Yes, I still curse checked exceptions on the daily. Yes, I still hate navigating my way through Boilerplate, because of course we have IDEs and LLMs generating our Boilerplate for us now. Yes, I find the streaming API clunky and annoying. Yes, I still get surprised by auto-boxing and unboxing. And yes, Project Valhalla took too long. And I haven't even mentioned some of the more annoying tooling, like the build tool Gradle and the object relational mapper Hibernate. Not to throw too much shade in their direction, it's just that they're tricky beasts to understand. And if you work on projects that need to be built, deployed, and connected to a database, well, you're probably going to encounter these tools and the mistakes of colleagues past. Yet, no matter how you feel about these tools, they are excellent examples of the healthy and mature ecosystem that surrounds Java. A programming language is just a software development project like anything else. The fundamentals are still true. You make decisions with the information that you have available at the time. And then time goes on and the information changes, and then more importantly, you change. Things that you thought were important no longer are, and instead of dying on hills, you choose your battles with more wisdom. Now, certainly when you're building a language and a runtime relied upon by millions of users for the integrity and performance of their software, then some of those decisions are naturally a little bit more permanent and harder to unravel. And if you spend more of your day formally proofing your solutions. But Java was 20 years old when Valhalla was announced. Maybe 20 years might have been a little bit too long to hold on to the mantra of everything is an object. And when you start a project, you can't always know what will come out of it. Sun started with the Green project, which yielded 6 prototypes of the Star 7 PDA. Now, who had heard of the Star 7 when I started this talk? Yeah, who had heard of Java? Right. So the fact remains that 30 years after its inception, Java is still running mission-critical systems all over the world, from financial institutions, e-commerce, telecommunications, healthcare, government, energy, utilities. It runs millions of Android devices, and the JVM supports dozens of languages that compile to Java bytecode, including my pet language, Kotlin. Oh yeah, and it pays my mortgage and has afforded me the opportunity to speak and receive healthcare from all over the world. Yeah. You can say the same for C#, that's fine. I mean, this isn't the case of either or. There's room in the world for both. So let's not get so emotional about the best way to tell a computer what to do. My name is Adele, and thank you so much for your time. So you can get the slides on the QR. There's also significant resources here. I didn't just make this up. I spent a lot of time in the Internet Archive. So if you do scan this QR, you get the slides and also that list of references. Thank you.